pi. What we have done up to now. We are trying to give some examples from practice. So we have examined the parallel adder here. Now we will be examining the don't care function type realization. This circuit is BCD accessory converter. I'm going to explain what it is, and we are going to do the design of it. And this is another 7-segment display driver. So I am going to give you the definition or word description of this circuit. So you could do your design after you learn this one. It becomes simpler. So let's go in detail. So I've got to switch it now to open board. So there's going to be a transform here, open board. Okay, here. So we are talking about now as circuit. The input of this circuit is binary coded decimal numbers. The output is binary coded decimal number plus 3. So this excess 3 comes from this 3. So if you remember what is binary coded decimal numbers are, we said to transfer the decimal numbers to binary base 2 binary numbers, it is difficult. Why is that? You've got to repetitively do the division operation and find the reminders. That's not an easy job to do, and it's difficult to do it in computer. Therefore, there is a simple conversion. What is this conversion? Just remind you, 975, this is a decimal number. In order to transfer to a binary number, you are transferring each digit in this decimal number to binary. So, and use 4 bits. So 5 is this, and 7 is 0, 1, 1, 1, and 9 is 1, 0, 0, 1. So this is 9, and this is 7, and this is 5. So that's binary number. So if normally you want to transfer this base 2, you're going to do 975 2, find the division and divide it by 2 again. As you know, you're going to do it. This is a difficult job to do. So let's come to the reality now. When we said binary coded decimal input is the input to this circuit, so you are talking about these digits in binary. So the highest number, the binary numbers that you're going to observe at the input of this circuit is in between 0 and 9, isn't it? In decimal number, in every digit, we've got these numbers only. We don't have 10, we don't have 11, we don't have 12, 13, 14, 15. We don't have these numbers as binary coded decimal because we don't see them as a digit in decimal numbers. Okay. Then, what we are saying, if you are writing a truth table, so for binary coded decimal numbers, between 0 and 1, these are all the corresponding binary coded decimal numbers to these decimal numbers. For those, in binary, this is equal to this one, but we don't see these numbers if they are binary coded decimal numbers. We don't see those. When you say we don't see those at the input of my circuit, the meaning for the output function is this. The output function values could be any value. That's why we put k's here. In Turkish, k is keyfi. In English, it says don't care function. So that means you don't care the function value for these non-applied inputs. So these are the don't care functions. Don't care functions. So part of this truth table has got unused inputs and the don't care values for the functions. So let's consider the other part of the truth table. This part, we're going to have output, and this circuit tells me whatever the input is, you're going to add 3 to that input and show it at the output. So for the 0 input, output is 3. For the 1 input, output is 4. For the 6 output, for the 6 input, output is 9. For the 9 input, the output is 12. So this is BCD excess-3 converter. So this tells me BCD excess-3 converter. These are the non-applied inputs, not applied inputs. Then don't care, outputs are the don't cares. So if we transfer the Carnot map, it's going to be like this. The Carnot maps are going to be like that. So let's examine this now. For example, the first function here has got 6 ones. So these are 1, 2, 3. Make it, so this one included in the function, right? And this one also. 6 of them. So the others are don't cares. So I can mark the don't cares with the green. Don't care 1, 2, 3, 4, 5, 6. So this is this 5, 6. Since the value of the function is not important, so that means you can choose these k's as you like. You can choose some of them as 0 and the others as 1. For example, if I choose this k equal to 0, this make a second order subcube here. If you choose it, second order subcube, that means prime implicant that you're going to choose the size of it. If you choose this one as 0, in the you are free to choose it. If you choose this k0, then this is going to be a first order subcube, one of them. This one and this one is going to be another subcube. So for this one, you're going to use 2 AND gate. Each of them has 3 fan-in. In here, you've got 1 AND gate, and fan-in is just 2. So what happened is this. By choosing this k equal to 1, I decrease the cost of my minimal function. Similarly, if you choose this k equal to 1, this makes a second order subcube, and you're going to choose these subcubes as 0. The other case is 0. So this is 0, that is 0, and that is 0. So you got one second order subcube here, another second order subcube here. So this 2 gives me that F3, that is. So this one then. So when you come to F4, that's quite interesting. Now the k positions are the same because for this function and this function, the k positions, they are all the same, so we keep it as it is. But in this case, I am choosing this k as 1, as like this one, but for this one, I have chosen x equal to k equal to 0 here, but it is k1 here. Why I have done this? Because if I choose this k1 and this k1, you're making a third order subcube. If we choose the other k's as 0, so you got these 6 ones here is in the original function here. What is F4? F4 here. You've got 6 ones here. And I added these 2 k's as equal to 0 as well. and I made a third order subcube. So this function is equal to f4. That's x4 prime. You see the x4 doesn't change. All the other variables are changing. So third order subcube, 3 variables disappear, just 1 variable in. Similarly to this one, so if you choose all the k's, in here we have chosen all the k's equal to 1 and make a third order subcube here, second order subcube here, another second order subcube here. Totally, I have got third order, 2 second order subcubes. Here you are. This is third order subcube, second order, second order. Summation of those 3 gives me F1. In here, once again, all the k's are chosen as 1. Then there is a subcube related to this one. This is essential prime implicant case. So there is a second order subcube here, maybe like a different color. So okay, this is the one color. So this here, make it clear. These two and these two. So that means dash case is its marked, isn't it? For this dash, here you are. So this is second order subcube, 2 variables disappears and just 2 left. So choose another color now. And in this case, I have chosen this and this after this k equal to 0. So this 2 and this 2 is another subcube, and that subcube is this one, right? And that is this one. You see the original function, that means this part of the truth table for the x2, f2, sorry. So here you are, these ones, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have chosen this k equal to 1, this one, and this k equal to 1. The others k's are, this k is also 1, the other k is 0, so that is 0 and that is 0. So I end up with this. So that is what was it? F2 function. So let me say the conclusion now. Conclusion is this. When you look at the one function here, which has got 6 k's in it, that means this function, this row, this column only, represent 2 to the power k number of functions. So these are the permutations of these k's, right? So among these 2 to the power k number of functions, since k is 5, there are 64 functions represented by this column. 64 functions, each of them has got minimal functions. So by choosing these k values, what we are doing is this. Among these 64 minimal functions, we are choosing the most minimal one by choosing these k values as we like. That's one conclusion. The second conclusion is this. If you're going to design more than one functions, as it is here, you are free to choose the k values, different values for each function. You don't have to choose the same k values for all the functions. You are free to choose the k values as you like. That helps to find the minimal out of minimal functions, to find the most minimal function among the 64 minimal functions. One thing more, so if you come a bit further, so these are the functions now. If you come to the realization level, after found the minimal functions, so these are the minimal functions up to here, minimal function here, 1, this is another minimal function, this is another minimal function. You could do some Boolean operations as we did here. After that operation, what you see, x3 and 4 is common here, is common here, is common here. So in this function, I have got two x3 functions, x3 plus x4 functions. So that means you can share these gates. Here you are, this gate x3 plus x4 gate. I am sharing this gate in this function and also in this function. So that means if you do the realization without considering this sharing business, you're going to end up with, for this one, two input AND gate 1, another two input AND gate, and one x1 is going to be connected to an OR gate, get F1. The second one, 3 input AND gate, the first one, and then 2 input AND gate, and a OR gate, that is F2. And this one has got two input AND gates and an OR gate, that is F3, and F4 is a NOT gate. So compare now this one, how many gates we have used, don't count the NOT gate, 1, 2, 3, 4, 5, 6, 7, 8, 8 here. Look at this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 here. So this is better than this one, isn't it? So what is the difference? At the end, if you're going to design more than one function, try to find out, is there any shared gate between these functions? If you find that, use that. That will decrease the cost of your design. So that is the end. Before we finish, I'll show you, just I am going to give you the word description of a 7-segment display driver. So you're going to do it your own. 7-segment display drivers use the how you're going to write the 7-segment in order to represent a decimal number. You could see these displays in calculators and traffic lights. So you see the decimal numbers there. So this driver, this circuit here, so this decimal number is, in each digit you got to show a number between 0 and 9. So that means all inputs are going to be BC, binary coded decimal numbers here. At the output, you're going to give this 7-segment. How we are going to say it? For example, look at this one. If you want to show LED is LED emitting diode. That is, when a voltage comes here, or in logical sense, if one comes to a LED, that LED lights. If it is, the input is 0, then it doesn't light at all. So that is how it works. So if you want to represent the 0, when the 0 input comes, 0, 0, 0 comes here, so you're going to, this F5 is not going to be on, the others are going to be on, isn't it? So that's going to be 1, 1, 1, 1, 1, 1. That means it is this, isn't it? So that is 0. This is not on. So you could see it here, 0, F3 is not on, the others are on. So you could write any number here. Let's say if you want to make it 8, isn't it? So all of them is going to be on. 8, all of them is going to be on. So you can figure out all the other numbers and fill in that truth table. So look at this truth table. Since we said only the binary coded decimal number is going to come in, that means the output values is not important, because the others, 10, 11, 12, 13, 14, 15 is not going to be applied. These are not going to be applied. So the outputs are not going to be observed at all. So all these are don't cares. So altogether we've got 7 don't care functions that we are going to design. This function is all of them are 4 variable functions. So design these 7 functions as we did it for BCD accessory converter. So this is maybe a homework. This is also a peer assignment type homework given to you, so you could do it to your hand. This is a good practice for you to do. So that's the end of this video then.